Hello friends, in today's video, let us do one problem related to the energy release in a fusion process. A deuterium reaction that occurs in experimental fusion reactor is H2DPH3 followed by H3DNHE4. Compute the energy release in each of these. Then compute the energy release per gram of the deuteron used in the fusion. Compute the percentage of the rest mass of deuteron released as energy, and finally compare uranium-235 fission with deuteron fusion as a source of energy release. We are given with some data. For example, the mass of deuteron is 2.014102 U. Then the mass of tritium is given by 3.016049 U, and the mass of a proton, which is 1H1, is equal to 1.007825. A mass of neutron is given by 0N1, 1.008665 U, and the mass of a helium is helium-4 is 4.002604, and finally the mass of uranium-235 is 235.0439. So let us move on to the problem. So first we need to compute the energy release in each of these. So first of all, let me introduce this notation of this nuclear reaction to you. So here this is another format of representing a nuclear reaction. So this means that a deuteron reacts with another deuteron to produce a tritium and a proton. So within these brackets, the first part will be the initial part, the initial nucleus that we will have, and the second one is the product. So if we write the first nuclear reaction, it will be like 1H2 plus another deuteron. Again, deuteron is 1H2. So 1H2 plus 1H2 gives a proton plus a tritium. That is the reaction. Gives a proton. How do you write proton? A proton is simply a hydrogen nucleus, which is 1H1 plus a tritium, which is 1H3, and plus a large amount of energy. So this is the first nuclear reaction that is written in another format. So let us calculate the energy released in this fusion process. So how do you calculate the energy? So we need to calculate the difference in mass between the final products and the initial products, and that difference in mass, the delta M, will be converted into energy according to the Einstein's relation. So first of all, let us calculate the delta M, the difference in mass. So the masses of the final particles are given by the initial mass minus final mass should be done, because initial mass is heavier. So the masses of the initial particles are the masses of neutron, which is 2.014102. So 2.014102 plus 2.014102. So this is the initial mass of the initial nuclei that we have, which is undergoing fusion. So the final mass, the mass of the final products is given by, we have a tritium whose mass is 3.016049, and the mass of the proton is 1.007825. So this is the total mass defect, this much AMU. So if it is converted into energy, how much energy will be that? So if you simplify this, it will be equal to 0.00433 U. So when two deuterium nuclei combine to form a proton and a tritium, the difference in mass between the initial and final parts, or the mass that is getting lost, is equal to 0.00433 AMU. So what will be the total energy released? So energy release will be multiply the difference in mass with the conversion factor, so 0.00433 multiplied by 931.5 or 931.3, that much amount of energy in mega electron volts. So this is equal to 4.032 mega electron volt. So in this fusion process indicated by this nuclear reaction, this much amount of energy will be released. Now moving on to the second reaction. Can you try to write the second reaction in this format, as a reaction format? So it will look like 1H3, initial nuclei are 1H3 and a deuteron. So they will be reacting. So 1H3 plus a deuteron is 1H2. It will give a neutron and a helium. So neutron is 0N1 plus a helium is 2He4 plus a large amount of energy. So how will you calculate the total amount of energy released in this process? First of all, calculate the difference in mass. The initial mass that we have is given by 3.016049 plus the mass of deuteron, which is 2.014102. So these are the masses of tritium and deuteron, minus the masses of the final particles, which are the helium and the neutron. Here it is, the mass of neutron is 1.008665 and the mass of the helium is 4.002604. So this much amount of atomic mass unit will be the total mass defect. So this will be equal to 0.018842 AMU. So that is the mass defect in this case. And what will be the energy released? Therefore, energy release can be calculated as multiplying the mass difference with the conversion factor 0.018842 multiplied with 931.3, which will give 17.58 mega electron volt. So in this nuclear fusion reaction, the total amount of energy released is 17.58 mega electron volt. So what is the total energy released in this fusion process? So when the final process happens, that means initially we have two deuterons which is combining to form a tritium and a proton, and this tritium is reacting with another deuteron to produce helium. So that is the overall process that is happening. And if you look at the overall process, effectively 3 deuterium nuclei are combining together to form a helium nucleus, 1 neutron and a proton. So that is the overall process that is happening. So how much amount of energy will be released in the overall process? So the total energy released in the overall process of the nuclear fusion of 3 three neutron nuclei is given by the sum of these two. First reaction will yield you 4.032 mega electron volt and the second reaction will yield you 17.58 mega electron volt, and hence the total amount of energy released is sum of those two factors, 4.032 plus 17.58, which is equal to 21.61 mega electron volt. So this much amount of energy will be released in the total reaction of combining together of 3 deuterium to form the helium nucleus, 2 He4, 1 proton and a neutron. So this is the overall process. You can try to write the overall reaction. The tritium term will get cancelled, and so the overall process is like this, and in this process the amount of energy released is 21.61 mega electron volt. So we have completed the first part of the question. Compute the energy released in each of these. We have calculated the energy released in the first reaction as well as the second reaction, and we have calculated the total amount of energy released in the whole process. Now we need to calculate the total energy released per gram of the neutron used in the fusion. So we know 3 deuterium combined to form a helium in this process, releasing 21.61 mega electron volt of energy. So what is the energy released per each nucleus? So we have section B, energy released per each nucleus. Per each of the neutron is equal to the total amount of energy released divided by 3, because combining together of 3 neutron will yield you 21.61 mega electron volt. So each neutron correspond to 21.61 divided by 3 MeV, which is equal to 7.203 MeV. So now we want to calculate the total energy released from 1 gram of neutron. So we need to know how many number of neutrons are there in 1 gram. So number of nuclei in 1 gram how do you calculate that? Because we know what does the Avogadro number represent? We know Avogadro number Na correspond to the weight of the nucleus or the weight of the atom represented in grams. For example, in the case of 1H2, the total mass is 2.014102 U. It is a very small quantity. It is very small. The power is 10 raised to minus 27. So we usually represent this unit in terms of gram. So if you represent the weight in terms of gram, that means you have to take Avogadro number of that nucleus or that atom. And hence, if you take 2.014102 gram of 1H2, you will have Avogadro number of 1H2. So if you take 1 gram of 1H2, how many number of nucleus will be there? It will be Avogadro number divided by the 2.014102 should be brought to the left side. So 2.014102. This much number of nucleus will be there in 1 gram of neutron. So if you calculate that, 1 gram of 1H2, the number of nucleus will be nuclei in 1 gram of 1H2 is equal to Avogadro number divided by 2.014102. So this much number of nucleus will be there in 1 gram of 1H2. If you take 2.014102 grams, there will be Avogadro number of nuclei. So if each of the nucleus will be releasing 7.203 MeV, then the total amount of energy released will be from 1 gram will be multiply 6.022 into 10 raised to 23 divided by 2.014102, which is the number of nuclei, into the energy released in each of the fusion. The energy released by each of the nucleus. 7.203 MeV is the energy released from 1H2 per 1H2. So multiply this with 7.203. This will yield you 2.153 multiplied by 10 raised to 24 mega electron volt. So this much amount of energy will be released if 1 gram of deuteron is made to undergo this reaction in 2 steps as mentioned earlier. So we have completed the B part B of the question. Now moving on to the part C. Compute the percentage of the rest mass of deuteron released as energy. So we need to know the percentage. So we know the energy released per fission or per 1H2 is 7.203 MeV. And what is the mass defect corresponding to this MeV? So the delta M corresponding to fusion per each 1H2. So if 7.203 MeV is released per 1H2 nuclei, that means the mass defect per each of the nucleus is 7.203 MeV divided by 931.3. If you know that mass defect, you will be multiplying by 931.3 to get the energy released. Now you know the energy released, so divide it by 931.3 to know the mass defect. So this much amount of AMU is the difference in mass per 1H2. Now what is the total mass? Mass of each 1H2 is 2.014102. So we know the difference in mass per 1H2 and we know the mass of 1H2. The question asks to find the percentage of the rest mass of deuteron released as energy. So out of this rest mass 2.014, this is the rest mass of deuteron. Out of this mass, this much amount is released as energy, is converted to energy. So what is the percentage? Divide each of them, find the ratio between them. So therefore, the percentage of the rest mass of deuteron released as energy. Released as energy. This is equal to the ratio between the mass difference, which is 7.203 divided by 931.3 divided by the initial rest mass, which is 2.014102. And this can be calculated. This is the ratio, and if you need to find the percentage, multiply this with 100. So this is equal to 0.348 3840 percentage. 3840 percentage. So if you take 100 percentage of a deuteron, out of this 0.38 percentage will be converted into energy in the mentioned nuclear fusion process. Now moving on to the last part of the question. Here we are asked to compare this fusion process with the uranium-235 fission process. So how much amount of energy is released in the nuclear fission of uranium-235? We have already calculated that the energy released per fission of each of the uranium-235 nucleus is actually approximately equal to 200 MeV. So if you calculate the percentage of mass that is getting converted into energy, percentage of mass of uranium-235 getting converted into energy, as done earlier, we need to calculate what percentage of the rest mass is converted into energy. So 200 MeV means what is the mass corresponding to 200 MeV? 200 divided by 931.3. This much is the difference in mass per fission. And what is the rest mass of uranium? Rest mass is 235.0439. This is just like the earlier example. We found the ratio of the mass that is converted into energy as a ratio. If this is the rest mass, out of this, how much mass is getting converted into energy? In the case of a deuteron, if 2.014 is the rest mass, out of this much fraction will be getting converted into energy. So just like that, in the case of uranium, which is releasing 200 MeV per fission, out of its rest mass, this much amount of mass is converted into energy. So multiply it with 100 to find the percentage, and this is equal to 0.09137. So if you compare the uranium fission and the fusion process, in the fusion of a deuteron, if you take 1 gram of deuteron, this much percentage of that taken mass will be converted into energy. That is a very huge amount of energy, right? So if you take uranium in the same amount, the mass conversion and then hence the energy released is lower. The percentage of mass that is converted into energy is just 0.09137. So if you find the ratio of energy release in the 1H2 fusion and the energy release in the uranium-235 fission, this will be the ratio of the percentages, which is 0.343840 divided by 0.09137, which is equal to 4.202. So if you take the same quantity of 1H2 and makes it to undergo fusion, and if you take the same quantity of uranium-235 and force it to undergo fission, we will get more energy from the fusion process. We will get as much as 4 times the energy released in a fission when we do the fusion process. So even though the energy released showed only 21.61 MeV per the total reaction, whereas in the case of uranium, the energy released is 200 MeV. You may think uranium will be releasing more energy by fission. But consider that uranium is heavier and has much more mass. So if you take same mass of uranium-235, which is undergoing fission, and deuteron, which is undergoing fusion, the deuteron fusion process will be releasing more amount of energy. So these are the concepts that we have discussed today. We have solved the problem. We have found the energy released in each of these reactions. Then we calculated the total energy, and then we calculated the percentage of the mass out of the rest mass that is being converted into energy, and we compared the fission reaction and the fusion reaction to find which one will be releasing more energy. So I hope this concept is clear for you. Thank you.